If f is a real-valued function of a variable x, then the graph of f describes a set in the xy plane where the vertical component of each point is determined by the value of f. In other words, along the graph, the y component is equal to f of x. Using graphs, it's possible to obtain all kinds of curves, including this v shape, which we'll recognize from a previous video as the graph of the absolute value function. One way of thinking about graphs is that drawing a graph describes a way of going from the data of a function to the data of a set in the plane. The resulting set in the plane, at least for functions in this course, is actually often a curve, meaning that it can be drawn with a single stroke of a pen. The vertical line test is a result that asserts when it's possible to undo this procedure of drawing a graph. That is, given the data of a curve in the xy plane, the vertical line test indicates when it's possible to find a function whose graph would produce that given curve. Precisely, the vertical line test says that a curve in the xy plane is the graph of a function of the variable x if and only if no vertical line intersects the curve more than once. The double-sided arrow used here indicates that the two statements on either side are equivalent to one another. That is, if one is true, then so is the other, and vice versa. This means that the vertical line test really contains two statements about a given curve in the xy plane. On the one hand, if the curve is a graph of a function of the variable x, then no vertical line intersects the curve more than once. On the other hand, if any vertical line intersects the curve more than once, then the curve is not the graph of a function. To see why this result is true, consider a curve in the plane, and suppose that the vertical line at x equals a intersects the curve more than once. Label the lower point of intersection a, b, and the upper point a, c. Now, if the curve were the graph of a function, say f, then f would have to be defined at the input a. Since the point a, b is on the graph, we know by definition of the graph that we must have f of a equals b, that is, f maps a to b. On the other hand, the point a, c being on the graph implies also that f of a equals c, that is, a maps to c as well. In order for f to be well defined, we would therefore need that b equals c, that is, the two outputs of f at a should be the same. But b being equal to c contradicts our assumption that b and c describe distinct points of intersection. As a specific example, consider the curve given by the unit circle in the plane. This is the circle of radius 1 centered about the origin. Explicitly, the curve consists of the set of points x and y, such that the relationship x squared plus y squared equals 1 is true. One might question whether this particular curve is the graph of a function of the variable x. The vertical line test allows us to quickly answer that question. Indeed, all we have to do is check whether there are any vertical lines that intersect the curve more than once. In this case, it's clear that there are many such vertical lines, and so the vertical line test implies that the unit circle is not the graph of a function. Since this curve isn't the graph of a single function, perhaps a better question to ask then is exactly how many graphs are needed in order to produce this curve? Because no vertical line intersects the curve more than twice, we realize that only at most 2 graphs are needed. Unfortunately, the vertical line test does not tell us explicitly how to describe these functions, but in this case, since we have an explicit formula for the curve, it's possible to construct these functions explicitly. In particular, the upper semicircle is described by the graph of the function f of x equals the square root of 1 minus x squared, and the lower semicircle by the graph of f of x equals minus the square root of 1 minus x squared. Notice that the curve y equals the square root of 1 minus x squared does indeed lie along the unit circle, because if we square both sides of this relation, then we get the relation y squared equals 1 minus x squared, which is equivalent to the relation describing the circle that we noted above. Perhaps it's interesting to note that recognizing the curve described by y equals the square root of 1 minus x squared as the upper semicircle offers a geometric way of determining the domain of the function defined by the square root of 1 minus x squared to be the closed interval from -1 to 1, a domain that we found by an algebraic method in a previous video.